The observer effect is one of the most intriguing, puzzling, and revolutionary concepts in all of science. It challenges our standard beliefs about how the universe works and forces us to rethink what it means to observe something. When we speak of the observer effect, we are referring specifically to a phenomenon in quantum mechanics that states, a quantum system behaves differently when it is observed or measured compared to when it is not. To understand this idea in depth, we need to explore what observation means in physics, why particles behave differently when measured, what scientific experiments led to this conclusion, and how this concept changed everything we thought we knew about matter, energy, and reality itself. The explanation is not simple because it overturns classical intuition, but once understood, it becomes one of the most beautiful insights into the nature of the universe. Why measurement in quantum mechanics is special in classical physics, which governs everyday objects like cars, planets, and falling apples. Measurement is passive. If you measure the speed of a car, you don't change its speed. If you weigh a rock, you don't alter its mass. Classical observation is like shining a flashlight on objects in a dark room. You illuminate them, but you don't change what they are. Quantum mechanics, however, takes place at a scale so tiny atoms, electrons, photons that the rules of classical physics no longer apply. At this microscopic level, particles do not behave like small balls or tiny pieces of matter. Instead, they behave like waves of probability. Their location, movement, spin, and energy level are not fixed. They exist in a superposition of possible states. This leads us to the first major idea behind the observer effect. Before measurement, particles do not have definite values. Instead, they exist as probabilities. Measurement forces the particle to choose one value. This forcing of a definite outcome is called wave function collapse. The wave function and its collapse, the wave function, is a mathematical description of a quantum system. It tells us everything that can possibly happen to that system and the probability of each outcome. Instead of saying, the electron is here, the wave function says, the electron could be here, or there, or somewhere else, until we measure it. When we measure the electron's position, its wave function collapses into a single location. Before measurement, many possibilities. After measurement, one outcome. This may sound abstract, but it has been tested and proven repeatedly through experiments. The observer effect is not a guess or a philosophical idea. It is measurable, repeatable, and forms the foundation of quantum physics. How do we know measurement changes behavior? To understand this fully, imagine trying to measure an electron's position. Electrons are incredibly small, so we need photons, particles of light, to detect them. But photons carry energy and momentum. When a photon strikes an electron to reveal its location, it pushes the electron, altering its momentum. This is an example of the observer effect. The act of measuring the position of an electron changes its motion. This difficulty is not because our tools are imperfect. It's because nature itself prevents us from observing without interacting. Every measurement involves energy exchange, and at the quantum level, that exchange changes the system. Heisenberg's uncertainty principle and the observer effect. The observer effect is closely connected to Heisenberg's uncertainty principle, which states, the more precisely you measure one property, like position, the less precisely you can know another, like momentum. This is not due to experimental error. It is a fundamental limitation built into nature. To measure position more accurately, you need higher energy photons. But those photons disturb the momentum of the particle even more. In simple terms, you can know where an electron is, but then you cannot know how fast it's moving. If you know how fast it's moving, you cannot know exactly where it is. Trying to observe one property automatically changes another. The double-slit experiment, the heart of the observer effect, the most famous demonstration of the observer effect, is the double-slit experiment. This experiment showed scientists that particles behave as waves when not observed and as particles when observed. Imagine firing electrons one at a time through two thin slits onto a screen. If unobserved, the electrons form a wave interference pattern, bright and dark bands, showing they act like waves passing through both slits simultaneously. But when detectors are placed at each slit to see which path the electron took, the wave pattern disappears. Instead, electrons behave like tiny particles going through one slit or the other. The act of observing destroys the wave-like behavior. The system behaves differently simply because we measured it. This experiment shows that unobserved electrons behave like waves. Observed electrons behave like particles. The observer effect is not a small disturbance. It is a total transformation of the particle's nature. Does this mean consciousness creates reality? This question often comes up, but the scientific answer is not necessarily. In physics, an observer is not a human mind. It can be any measuring device, a detector, a sensor, or any interaction that causes information to be recorded counts as an observation. Consciousness is not required. However, the strange behavior of particles has led to debates among physicists and philosophers. Some interpretations suggest consciousness might have a unique relationship with measurement. Others argue that measurement simply means any interaction that leaves a trace in the environment. Regardless of philosophical interpretations, the scientific fact remains. A quantum system behaves differently when it is measured. Why quantum measurement changes behavior at the quantum scale? There is no such thing as observing without interacting. Measurement means interacting, and interacting means influencing. Photons, electrons, atoms, all exert forces, create collapses, and exchange energy. Consider these examples. To observe an electron's location, we need photons. To detect a photon's path, we need sensors that absorb or scatter it. To measure a nucleus's spin, we use magnetic fields that influence it. In every case, the measurement tool becomes part of the system. The line between system and observer dissolves. Why this breaks classical thinking in classical physics? Objects have fixed properties. Observation is passive. The world exists independently of measurement. In quantum physics, properties exist only as probabilities. Observation is active. Measurement determines certain aspects of reality. This doesn't mean the observer creates the universe. It means the act of measurement transforms the system from potential to actual. The observer effect in modern technology, many technologies rely on the observer effect. Quantum computing uses quantum states that collapse when observed, which is why qubits cannot be directly measured without losing information. Quantum cryptography relies on the fact that observing a quantum message disturbs it, revealing eavesdropping. Electron microscopes use the interaction between electrons and objects to form images. These technologies prove that the observer effect is not theoretical. It is a fundamental part of how the universe works. Why the observer effect matters? The observer effect teaches us that the universe is not a static place filled with objects that behave independently. Instead, reality is dynamic, probabilistic, and influenced by interactions. At the quantum scale, the universe does not reveal itself passively. It responds to our attempts to measure it. This challenges our intuition, but opens the door to deeper understanding. The observer effect is not just a scientific concept. It is a doorway to the mysteries of existence itself. The observer effect becomes even more fascinating when we explore its deeper implications and the broader scientific landscape it transforms. One of the most important aspects of this effect is its challenge to classical determinism. Classical physics, the science that reigned from Newton's era to the early 20th century, was built on the belief that the universe operates like a giant machine. If you knew the position and speed of all particles in the universe, classical physicists believed you could predict everything that would ever happen, every movement, every reaction, every future event, but the observer effect shattered that world view. It introduced a fundamental randomness into the fabric of reality. Even if we knew everything about a particle's wave function, we could only predict probabilities, not certainties. Measurement doesn't reveal a pre-existing truth. It creates an outcome from a set of possibilities. This brings us to a critical insight. Measurement doesn't simply uncover properties. It helps define them. Before observation, quantum systems do not have definite positions or momenta. They exist as mixtures of states, described by a wave function. When we interact with the system, the wave function collapses into a specific value. It is as if nature refuses to reveal its hand until the moment we look. But why does nature behave this way? Why would particles exist in a state of probability rather than certainty? Physicists don't agree on the answer. There are multiple interpretations of quantum mechanics, each attempting to explain the observer effect in its own way. The Copenhagen interpretation, which is one of the oldest and most widely taught explanations, states that quantum particles exist as waves of probability until observation forces them into a definite state. This approach avoids asking deeper metaphysical questions about what the particles really are before observation, focusing instead on what we can measure. On the other hand, the many worlds interpretation suggests that the wave function never collapses at all. Instead, every possible outcome happens in a branching multiverse. In one universe, the particle goes through the left slit. In another, it goes through the right. In one branch, the detector clicks. In another, it stays silent. According to this interpretation, measurement doesn't collapse reality, it splits it. The observer effect, in this view, is simply our experience of becoming correlated with one branch of the universal wave function. Another interpretation comes from de Broglie and Bohm, who proposed a pilot wave theory. This approach claims that particles have real positions at all times, guided by a hidden wave. Observation does not create reality, but reveals one part of a deeper, hidden order. This interpretation removes randomness in principle, but introduces non-locality, meaning that actions in one place can instantly influence distant regions, something Einstein famously disliked, calling it spooky action at a distance. Yet experiments on quantum entanglement, such as those by Bell and Aspect, have shown that the universe indeed contains non-local behavior. These experiments strengthen the idea that measurement has profound consequences, influencing even particles that are far apart. As we explore these interpretations, the observer effect becomes more than a laboratory phenomenon. It becomes a window into how reality operates. Is the universe fundamentally probabilistic or deterministic? Do probabilities collapse or do realities split? Is measurement a physical event, an informational event, or something else entirely? These questions show that the observer effect is not merely about what happens in experiment. It is about the nature of existence. The role of information in the observer effect has also gained immense attention. Some physicists, like John Archibald Wheeler, introduced the concept of it from bit, proposing that information is the foundation of reality. In this framework, every physical event arises from binary yes/no decisions. Measurement is the process of acquiring information, and this informational act shapes the physical world. For example, when a particle is in superposition, it represents incomplete information. When observed, the act of gathering information collapses that uncertainty into a definite result. This perspective suggests that measurement is not about consciousness, but about information flow itself. If information becomes available even to a non-conscious device, that is enough to collapse a wave function. This emphasis on information brings us to quantum decoherence, a modern theory that explains how interactions with the environment cause wave functions to collapse. A quantum system is extremely delicate. It can remain in superposition only if it is isolated from everything else. The slightest interaction, light hitting it, air molecules colliding with it, or a detector absorbing a photon, causes decoherence, which converts the system from a spread-out wave of possibilities into a definite outcome. Decoherence doesn't solve all mysteries, but it shows that the environment acts like an observer. The universe is full of interactions, and these interactions continuously collapse quantum possibilities into classical reality. This blending of quantum and classical physics is essential to understand why we do not experience quantum uncertainty in daily life. We never see chairs in superposition, or cats both alive and dead, because these large objects interact constantly with their environment. Their quantum states decohere too quickly to maintain superposition. This means the observer effect is not limited to laboratories. It is happening everywhere, all the time. Every time a particle interacts with anything, information is exchanged, and probabilities become realities. The observer effect also has profound implications for understanding time. In quantum physics, time is usually treated as a background parameter, not as a dynamic part of the system. But some theories suggest that measurement may play a role in how time flows. Before measurement, the wave function evolves smoothly, deterministically. After measurement, the wave function collapses abruptly. This sudden collapse could be seen as a moment where the universe chooses a path among many. Some physicists propose that these choices give rise to our experience of time moving forward. Without measurement, time might not function the way we understand it. This perspective opens up philosophical questions about whether time itself may depend on observation. Another important aspect of the observer effect is its relationship with quantum entanglement. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. This instantaneous connection defies classical physics and suggests that measurement has consequences that ripple across the universe. Imagine two entangled electrons created together. If you measure one electron's spin and find it spinning up, the other electron instantly becomes spin down, even if it is on the opposite side of the galaxy. This is not communication in the classical sense. No information is transmitted faster than light. Instead, it shows that entangled particles share a unified quantum state. When measurement collapses one part of the state, the other part collapses simultaneously. Here again, measurement transforms the system. The observer effect also reshapes our ideas about objectivity. In classical science, objectivity is the belief that the universe behaves the same regardless of who observes it. But quantum physics suggests that different observers can see different realities if they measure different aspects of the system. For instance, Two observers measuring entangled particles may obtain correlated results, even if their measurements are independent. In some cases, what one observer considers real depends on what another observer measures. This interdependence challenges the classical idea of a single observer, independent reality. Some physicists propose the relational interpretation of quantum mechanics, which claims that reality is not absolute but relational. In this view, properties of a quantum system only exist relative to a specific observer. Two observers may describe the same system differently, and both descriptions can be valid. Reality becomes a network of relationships, not a fixed set of objects. Measurement is the process that defines these relationships. The observer effect, therefore, is not a disturbance of reality. It is part of how reality is constructed. The observer effect even has consequences for cosmology and the origin of the universe. Some scientists argue that in the earliest moments after the Big Bang, quantum fluctuations were amplified into the structures that became galaxies and stars. These fluctuations existed in superposition until interactions in the young universe caused decoherence, shaping the cosmic landscape. In this sense, the universe observed itself into structure. The early universe was a quantum system undergoing measurement through interactions and information exchange, giving rise to the world we see today. Another area influenced by the observer effect is quantum biology, a relatively new field exploring whether biological systems use quantum effects. Some researchers believe that processes like photosynthesis, bird navigation, enzyme activity, and even human cognition may involve quantum coherence and measurement, like interactions. For example, some birds appear to navigate using entangled particles affected by Earth's magnetic field. These ideas are still under investigation, but they suggest that the observer effect might play a role in how life processes information. The question of consciousness sometimes returns to the discussion. While mainstream physics does not claim that consciousness collapses wave functions, some theories explore whether the brain might be sensitive to quantum effects. The Penrose, Hameroff-Orch or theory, for example, suggests that microtubules in neurons may host quantum states that collapse in a way that contributes to conscious experience. This idea remains controversial, but it highlights the ongoing interest in the connection between measurement and awareness. Whether or not consciousness plays a direct role in quantum processes, it is undeniable that consciousness plays an interpretive role. We are the ones who make sense of measurement results. The observer effect also raises ethical and philosophical questions. If measurement helps define reality, what is the role of human inquiry? Does observation carry responsibility? How much of reality is shaped by our interaction with it? These questions do not imply that humans control the universe. Rather, they emphasize that we are active participants in understanding it. Measurement is an interaction, and interactions change the universe in measurable ways. Finally, the observer effect encourages humility. It reminds us that nature is not obligated to match our expectations. For centuries, humans believed that reality was straightforward, predictable, and independent of our actions. Quantum mechanics revealed that the universe is far more subtle, interconnected, and mysterious. Measurement is not a simple act of seeing. It is a physical event that transforms systems, reveals hidden potentials, and defines outcomes. It forces us to acknowledge that the universe is not a static object, but a dynamic interplay of possibilities and interactions. The observer effect, at its core, teaches us that by observing the world, we become woven into its fabric. Quantum mechanics introduced one of the most extraordinary concepts in the history of science: the idea that particles do not have fixed properties until they are observed. Instead, they exist in a superposition, a combination of all possible states simultaneously. This principle forms the foundation of modern physics and dramatically separates the quantum world from the classical world we experience in everyday life. To understand this keynote in depth, we must examine what superposition truly means, how it was discovered, why particles behave this way, and what implications it holds for nature, technology, and philosophy. The idea that a particle can exist in multiple states at once seems impossible from a classical point of view. A ball cannot be in two places at the same time. A car cannot move in two different directions simultaneously, and a cat cannot be both awake and asleep at once. Yet, at the atomic and subatomic levels, electrons, photons, protons, atoms, and even molecules behave in ways that challenge our intuition. They exhibit behaviors that only make sense if they exist as waves that spread out, interfere, and combine. A wave does not occupy one single location. It extends across space. Similarly, a particle in quantum superposition is not in one definite state, but in many, each with a certain probability. One of the earliest hints of superposition came from studying light. In the 19th century, Thomas Young's double-slit experiment demonstrated that light behaves like a wave. When a beam of light is split into two paths and recombined, it creates an interference pattern of bright and dark bands. This pattern only occurs when different parts of the wave interact with each other. But early 20th century experiments showed that light is also made of particles called photons. How can something be both? Quantum mechanics solved this paradox. Photons exist as wave-like probabilities until observed. Only when measured do they display particle-like behavior. This realization became a cornerstone of the superposition principle. Electrons learned to surprise scientists in the same way. When electrons are fired toward a double-slit apparatus one by one, they still form an interference pattern even though each electron is traveling alone. This means that each electron behaves like a wave that passes through both slits simultaneously. It is not that the electron chooses one slit or the other. Instead, it exists in a superposition of went through the left slit and went through the right slit. Only when we place detectors at the slits does the electron choose a single path, collapsing its wave function and destroying the interference pattern. This is the heart of superposition. Before observation, the electron is in all possible states. After observation, it collapses into one specific state. This collapse is often misunderstood. It is not a physical explosion or destruction of a wave. Rather, it is a change in the mathematical description of the system. The wave function, which encodes all possible states and the probabilities of observing them, transitions from spreading across many states to selecting one based on probability. The collapse reflects the creation of information. When we measure, we obtain a definite answer, and the system chooses a definite condition. One way to imagine superposition is to picture a spinning coin. When the coin is spinning, it is neither heads nor tails. It is in a blend of both states. Only when it lands does it choose one. But superposition is more profound than this analogy. A spinning coin is in an uncertain state because of our lack of knowledge, not because it is literally both heads and tails at once. In contrast, a quantum particle in superposition truly occupies multiple states simultaneously, not because we lack knowledge, but because that is its fundamental nature. A more accurate metaphor is a musical chord. To the ear, a chord is multiple notes played at once, each contributing to the sound. If we analyze the chord mathematically, we find it is the sum of several frequencies. Likewise, a quantum particle in superposition is the sum of multiple possible states. But unlike a chord, which we can hear all at once, the quantum particle collapses to a single note when measured. The mathematics of superposition involves vectors in a multidimensional space called Hilbert space. Each possible state of the system corresponds to a vector, and superposition is a combination of these vectors. The wave function assigns amplitudes to each state, and the amplitudes determine the probabilities of each outcome. The collapse projects the wave function onto a single basis vector, corresponding to the observed result. Though this mathematical explanation may sound abstract, it is essential for explaining why quantum technologies like quantum computing work. Quantum computers store information in qubits instead of classical bits. A classical bit is either 0 or 1. A quantum bit, however, can be 0, 1, or any superposition of both. This allows quantum computers to perform many calculations simultaneously, giving them enormous potential for solving problems impossible for classical machines. Superposition is not just a philosophical curiosity, it is the fuel of next-generation technology. To illustrate superposition in detail, imagine an electron in an atom. Classical physics might say the electron orbits the nucleus the way a planet orbits the sun. Quantum mechanics tells us something completely different. The electron does not move on a fixed path. Instead, it exists as a cloud of probability around the nucleus. This cloud is not a literal cloud. It represents the distribution of possible locations where the electron might be found if measured. The electron does not occupy one point until measurement forces it to adopt one. This means that every electron in an atom is in superposition all the time. It occupies many positions simultaneously. It also has many possible energies, spins, and momenta at once. Only when we measure any one of these properties does the superposition collapse into a definite value. The rest of the properties remain in superposition until measured. Some of the strangest experimental demonstrations of superposition involve large molecules like buckyballs, which contain 60 carbon atoms. Researchers have shown that even such large objects can form interference patterns, proving they exist in superposition before observation. This suggests that superposition is not limited to tiny particles. It applies to larger systems as well. The reason we do not see chairs and humans in superposition is due to decoherence, where interactions with the environment cause superposition to collapse extremely quickly. But at the fundamental level, everything obeys these quantum laws. The concept of superposition inspired one of the most famous thought experiments in history, Schrödinger's cat. Erwin Schrödinger imagined a sealed box containing a cat, a radioactive atom, a detector, and poison. If the atom decays a quantum event, the detector breaks the vial, releasing poison and killing the cat. If the atom does not decay, the cat lives. According to quantum mechanics, the atom exists in a superposition of decay and no decay until observed. Thus, the cat is in a superposition of alive and dead until the box is opened. Schrödinger did not propose this thought experiment to suggest cats really behave this way. He wanted to show how absurd quantum mechanics appears when applied to everyday objects. Yet the experiment illustrates the central idea. Superposition persists until measurement, and collapse happens only when information becomes available. Superposition also leads to quantum entanglement. When two particles interact and become entangled, their combined state is described by a single superposition. Measuring one collapses the entire system, making the other particle adopt a corresponding state instantly. The famous Einstein-Podolsky-Rosen-Epper paper argued that this phenomenon implies quantum mechanics is incomplete. Einstein disliked the idea of instantaneous effects across distance, calling it spooky action at a distance. However, experiments have repeatedly confirmed entanglement, showing that superposition applies not just to individual particles, but to entire systems of particles. In recent years, physicists have successfully created superpositions of even larger systems, like small mechanical resonators and superconducting circuits. These experiments show that superposition is not merely a theoretical construct. It is a real physical phenomenon that we can control and measure. It also plays a role in the emerging fields of quantum sensing and quantum communication, where superposition allows for extremely precise measurements and secure transmission of information. We must also consider the philosophical implications of superposition. Many interpretations of quantum mechanics attempt to explain what superposition means in reality. Some argue that superposition reflects our lack of information. Others claim the wave function is a physical object. Still others suggest that many worlds exist, each representing one possible outcome. No single interpretation has gained universal acceptance, because all interpretations make the same predictions experimentally. Superposition challenges the idea that the world is made of objects with fixed properties. It suggests that the universe is made of possibilities, and reality emerges only when possibilities collapse under observation. This does not mean the universe is imaginary or subjective. It means that certainty and definiteness arise from interaction. In the quantum realm, potential is just as real as actuality. The line between what is and what could be becomes blurred. Superposition also raises questions about free will and determinism. If particles exist in multiple states until measured, is the universe fundamentally open-ended? Are outcomes chosen randomly, or does some deeper law govern their collapse? These questions remain unsolved, making superposition one of the most profound and mysterious principles in science. Superposition even affects our understanding of identity. If quantum systems exist as blends of states, what does it mean to say that a particle is something? Identity becomes fluid. A particle is not something with definite features, but a wave of potential outcomes. This perspective may have implications for fields such as consciousness studies, information theory, and the nature of time. Building upon the foundational ideas already introduced, the next phase of the explanation focuses on how electrical quantities behave inside a branching network, and how these behaviors influence the performance, stability, and predictability of real-world circuits. The emphasis here is not merely on formulas or mathematical rules, but on the deeper conceptual understanding of how currents and voltages spread, adapt, and balance themselves throughout interconnected pathways. RBSPECTFUL null vital in fields ranging from basic electronics to advanced power distribution, communication engineering, robotics, automotive systems, and integrated circuit design. At the core of this deeper understanding is the idea that current is a dynamic response of charges seeking the easiest pathway while maintaining overall equilibrium. When a conductor divides into multiple branches, the flow of charges distributes itself in a way that respects the physical structure of the network. This distribution is not random, it is governed by the electrical effort, required to move through each path. A lower effort, lower opposition invites more charge flow, while a path with higher opposition receives less. This natural self-organization of charge movement is what allows complex circuits to operate smoothly, even when containing numerous components, loads, and interconnections. To visualize this behavior more intuitively, imagine water flowing through a pipeline that suddenly splits into several channels. If one channel is wide and smooth, more water will pass through it. If another is narrow or partly blocked, less water will go that way. Yet in the end, the total water entering the split must equal the total water coming out, because there is nowhere else for it to go. In electrical terms, the flow of charge behaves the same way. The distribution may change, but the overall balance remains intact. This balance is essential to ensure that devices connected to the circuit receive consistent power and function without instability. A branching electrical network also behaves like a dynamic negotiation system. Each branch requests a certain amount of current depending on its load, and the energy source satisfies those requests as long as it has the capacity. For example, a branch with a heavy load demands more current, while one with a lighter load requires less. The system balances these demands automatically. The presence of multiple branches does not confuse the electrical source. Instead, it divides current proportionally based on the physical characteristics of each path. But this distribution process does not occur in isolation. It directly interacts with voltage behavior throughout the network. Voltage acts like the driving force that pushes charges along a conductor. When branches form, each branch must experience conditions that allow charges to flow in a stable manner. These conditions are determined by the potential differences across the network. In a branching point, voltage becomes the pressure, trying to move charges forward. If multiple branches exist, the driving pressure across each branch remains aligned because the circuit seeks consistent energy distribution. The fascinating aspect is that branches do not create extra energy, nor do they reduce the total energy provided by the source. Instead, they divide the existing energy across different paths based on the electrical characteristics present. This division can change the experience of individual components, but the overall electrical system remains in harmony. Devices connected in separate branches receive energy without interfering with each other, provided the system is designed properly. This is essential for ensuring that electronics can power multiple devices simultaneously: lights, motors, sensors, speakers, processors, and displays, all from the same supply. The behavior of current at intersection points becomes even more important as circuits grow more complex. Modern systems such as smartphones, computers, cars, and industrial controllers contain thousands or millions of branching points. Each one must handle current distribution correctly to avoid malfunction, overheating, or inefficiency. The elegance of these systems is that even with so many branching pathways, the flow of charge remains predictable as long as the network is understood and the interconnections follow consistent rules. When examining a branching point, it becomes clear that each branch acts like a temporary host for the flow of electrical charge. Charges arrive, choose a path based on the electrical cost, and move forward. Once they complete their journey, they either return to the energy source or continue to another stage of the circuit. This balanced flow ensures continuity, meaning every unit of charge that enters a node must leave it somewhere. If this did not happen, charge would accumulate indefinitely, which is physically impossible in a steady-state circuit. This is why electrical systems remain stable, and do not randomly build up excess charge at connection points. Another important aspect of this keynote is how interference is avoided. When multiple branches exist, charges must not collide or contradict each other's movement. Instead of chaos, what happens is a remarkable organization where every electron contributes smoothly to the collective flow. This harmonized behavior is made possible by the consistent potential levels across the circuit. The potential difference ensures that charges always know which direction to move in and how strongly to move. As long as the potential difference is maintained, the system remains functional, regardless of the number of branches. In practical applications, understanding the flow of current through branching networks becomes critical for safety. If one branch demands too much current compared to what the conductor can handle, the wire may overheat. Engineers must therefore design circuits that properly distribute load. This involves selecting appropriate conductor sizes, ensuring that branches do not exceed safe limits, and including protective devices such as fuses and circuit breakers. These elements monitor the flow and intervene when a branch exceeds its intended capacity. Without such measures, electrical fires or equipment damage could result. Another key factor in branching networks is their effect on component performance. For example, a sensor connected in one branch might require precise voltage conditions to operate correctly, while another branch might power a motor that produces electrical noise. If the network is not arranged properly, the noise from one branch could interfere with the operation of the sensor in another branch. Effective circuit design must therefore ensure that sensitive components receive stable and clean power. This is achieved by controlling how branches are arranged, sometimes separating high power and low power lines, or adding filtering components to absorb unwanted fluctuations. Branching networks also play a major role in energy efficiency. A poorly designed branching system may cause unnecessary losses, causing the power source to work harder than necessary. Efficient distribution ensures that each branch receives only the energy it requires without introducing unnecessary drain. In large-scale systems such as power grids, this principle becomes vital. Electrical transmission lines use branching concepts to distribute power to entire cities. The same rules that govern small circuits inside electronic devices also govern massive distribution networks spanning hundreds of kilometers. Within digital circuits, branching plays a different but equally significant role. Modern processors operate by rapidly directing electrical signals through millions of microscopic pathways. Each pathway acts like a branch, carrying information rather than raw power. The timing, stability, and reliability of these branches affect computing speed and accuracy. Even though the currents involved are extremely small, the fundamental behavior remains identical. Signals entering a branching point must distribute correctly and reach their intended destinations without loss or interference. Another area where the understanding of branching behavior becomes crucial is in fault analysis. When something fails in a circuit, one of the first questions engineers ask is how the failure affects current distribution. A branch may become open, no current, or shorted, too much current, causing abnormal flow in the rest of the circuit. By understanding how current normally divides at branching points, engineers can quickly identify where a fault likely occurred, why it happened, and how to fix it without disassembling the entire system. From a theoretical perspective, branching systems help illustrate fundamental principles about conservation, equilibrium, and energy flow. They show how nature organizes even the smallest particles to behave predictably under the influence of electrical forces. The smooth balancing of charge movement at branching points provides insight into how order arises naturally in physical systems, even when many pathways are involved. From a practical perspective, mastering the behavior of current in divided pathways allows one to design anything from simple home circuits to advanced industrial machinery, communication networks, and microelectronics. Understanding these concepts provides the foundation for troubleshooting, designing efficient systems, and ensuring long-term reliability. The double-slit experiment is one of the most fascinating and important demonstrations in modern physics because it shows that light and matter do not behave in a single, predictable way. Instead, they display two different behaviors, wave-like and particle-like, depending on how they are observed. This strange shift in behavior is at the heart of quantum mechanics, a field that describes how nature works at extremely small scales. Understanding the double-slit experiment gives us a window into a world where ordinary intuition no longer works, and where reality behaves in surprising and mysterious ways. To understand the significance of this experiment, imagine shining a beam of light at a barrier with two narrow openings, slits. Behind the barrier is a screen that records where the light lands. If light behaved strictly like tiny particles, we would expect the screen to show two bright bands, one behind each slit, exactly like throwing small stones through two openings. But if light behaved as a wave, the result would be entirely different. A wave passing through two gaps spreads out, and the two spreading waves overlap. Where the crests of the waves meet, they reinforce each other and create bright bands. Where a crest meets a trough, they cancel and create dark bands. This pattern of alternating bright and dark regions is known as an interference pattern, and it is a clear signature of wave behavior. When the double-slit experiment is first performed using light, the screen indeed shows an interference pattern. This means the light behaves like a wave, spreading out and interfering with itself. This was already surprising in the early days of physics, because light had long been debated as being either a stream of particles or a wave. The double-slit experiment offered strong evidence for the wave theory of light. The mystery deepened when scientists repeated the same experiment using particles such as electrons. Electrons are usually thought of as tiny bits of matter, like miniature particles. If electrons were strictly particles, we would expect to see two clusters on the screen, each behind one slit. But shockingly, even electrons created an interference pattern, the same kind of pattern that waves produce. This suggested that electrons, which we often consider as particles, also behave like waves. But the experiment became even stranger when scientists reduced the number of electrons being fired. Instead of firing a continuous stream, they released electrons one at a time, ensuring that each electron passed through the slits alone. You would expect a single particle to choose one slit and behave accordingly. But even when electrons pass individually, over time they still form an interference pattern on the screen. This seems to imply that a single electron behaves like a wave, passes through both slits at the same time, interferes with itself, and then lands on the screen. This is one of the most mysterious findings in physics. It shows that electrons cannot be described simply as particles. They carry wave-like properties even when they are alone. However, the story does not end here. The most remarkable part is what happens when we try to observe the electrons more closely. Scientists wanted to know how electrons manage to go through both slits at once. So they placed measuring devices at the slits to determine which slit an electron actually passes through. What they found was astonishing. The moment they observed the electrons, the interference pattern disappeared. Instead of wave-like behavior, the electrons suddenly behaved like particles. The electrons passed through one slit or the other, and the pattern on the screen showed two clusters instead of interference bands. This dramatic change in behavior triggered a major shift in physics. It showed that the act of measurement, simply observing, affects how nature behaves. When undisturbed, electrons behave like waves, spreading out and interfering. But when observed, they behave like particles, passing through one slit only. The experiment demonstrates that the nature of light and matter is not fixed. Instead, it depends on the experimental conditions, especially whether measurement is taking place. This phenomenon is called wave-particle duality. The term means that quantum objects such as photons, light particles, and electrons exhibit both wave-like and particle-like properties, and the observed behavior depends on how we try to measure them. When we do not measure which slit the object passes through, we see evidence of its wave-like nature. When we attempt to measure its path, the wave-like behavior collapses and particle-like behavior emerges. But why does simply observing change the outcome? The answer lies in the principles of quantum mechanics. In the quantum world, particles do not have definite positions or paths until they are measured. Before measurement, they exist in a state called a superposition, where they occupy multiple possibilities at once. In the double-slit setup, an electron in superposition behaves like a wave passing through both slits simultaneously. Measurement forces the electron to choose one of the possible paths, collapsing the wave into a single particle-like state. This collapse eliminates interference, and the electron then behaves like a classical particle. The double-slit experiment thus reveals that the fundamental building blocks of the universe do not behave like the familiar objects we interact with daily. They do not have definite positions, paths, or states until someone observes them. This raises profound questions about the role of the observer in physics, the nature of reality, and whether the universe exists in a definite state when not being observed. Moreover, the experiment shows that classical physics, the physics that explains everyday motion, mechanics, and light, cannot fully describe nature at tiny scales. Instead, a new framework, quantum mechanics, is necessary to understand how particles behave. The double-slit experiment is often described as the experiment that changed everything, because it revealed behaviors that defy classical explanation. In summary, the statement, the double-slit experiment demonstrates the shift from wave-like to particle-like behavior, refers to how quantum objects change depending on observation. Without measurement, they behave like waves and create interference patterns. With measurement, they behave like particles and lose their wave-like interference. This experiment beautifully captures the essence of quantum mechanics, the dual nature of light and matter, the role of observation, and the mysterious and counterintuitive behavior of the microscopic world. Observation in physics does not require human consciousness. Any measuring device counts. In quantum mechanics, the concept of observation often leads to confusion, largely because of the philosophical implications of measurement. Many people assume that the act of observing something requires a conscious mind, but in physics, this is not the case. Observation is defined much more broadly. It is any interaction between a quantum system and an external device or environment that produces a measurable outcome. This understanding is crucial because it clarifies the role of measurement in quantum experiments and separates physical reality from human perception. The idea begins with the fundamental principles of quantum mechanics. Quantum systems, such as electrons, photons, and atoms, exist in superpositions of multiple possible states before measurement. The act of measurement causes the wave function, a mathematical description of all possible states, to collapse into a single outcome. This collapse is not triggered by human thought or awareness. It is triggered by the physical process of interaction between the system and a measuring device. In other words, a detector, a sensor, or even another particle that interacts with the system can function as an observer. Consider the double-slit experiment, a cornerstone demonstration in quantum physics. When photons or electrons pass through two slits without any measurement devices in place, they form an interference pattern on the screen behind the slits, demonstrating wave-like behavior. This pattern appears even if the particles pass through the slits one at a time. However, if detectors are placed at the slits to determine which path a particle takes, the interference pattern disappears and the particles behave like classical particles. This change occurs regardless of whether a human is watching the detectors or not. The mere presence of the measurement apparatus, the detectors interacting with the particles, is sufficient to collapse the wave function and produce a definite outcome. The fact that observation does not require consciousness is supported by numerous experiments. In quantum mechanics, measurement can be defined as any process that leaves a record in the system or its environment. For example, a photon striking a photographic plate or an electron interacting with a sensor causes an irreversible change in the state of the apparatus. This change encodes information about the quantum system. Human awareness is unnecessary. The physical recording itself is sufficient. The system has been observed in the physical sense because information about the system's state has been transferred to another system. This perspective is reinforced by the concept of quantum decoherence. Decoherence occurs when a quantum system interacts with its environment, causing the superposition of states to appear to collapse into a classical mixture of outcomes. In practical terms, even if no person is consciously measuring the system, the environment itself acts as a vast network of measuring devices. Molecules, photons, air particles, and other environmental factors all continuously interact with quantum systems. These interactions effectively observe the system by entangling with it and dispersing information into the environment. The result is the appearance of wave function collapse, even without any conscious observer. A concrete example is a particle in a box exposed to light. Photons in the environment constantly bounce off the particle. Each interaction transfers information about the particle's position to the surrounding environment, causing decoherence. This is why macroscopic objects, like chairs and tables, do not display superposition in everyday life. They are continuously observed by their environment. No conscious mind is involved. The interaction alone ensures that classical reality emerges from quantum uncertainty. Another important point is that treating human consciousness as a requirement for measurement introduces unnecessary complications. If consciousness were necessary, then quantum systems would remain in indefinite states whenever no human is observing them, implying a universe that only exists when perceived. This notion is highly counterintuitive and unsupported by empirical evidence. Experiments and theoretical work show that quantum systems evolve and interact independently of observers' minds. The universe does not wait for a human to look at it. It behaves according to physical laws. Many interpretations of quantum mechanics reinforce this view. The Copenhagen interpretation, one of the most widely taught frameworks, describes measurement as a physical interaction that produces a definite outcome. It does not require human awareness. The many worlds interpretation also avoids invoking consciousness, suggesting that every possible outcome occurs in a branching universe. Observation simply correlates an observer with a particular outcome. Even more modern interpretations, such as quantum decoherence theory, explain the apparent collapse of the wave function entirely in terms of environmental interactions, without any need for conscious involvement. It is also worth considering the role of modern experimental apparatus. In contemporary laboratories, quantum measurements are often automated. Detectors record outcomes, data is collected digitally, and no human is present during the measurement process. The results still demonstrate wave function collapse and particle behavior exactly as predicted by theory. This fact confirms that physical interaction, not consciousness, is sufficient to produce observable quantum phenomena. The misconception that observation requires consciousness likely arises from a combination of language and early philosophical speculation. Popular descriptions sometimes use words like observer or measurement in ways that sound like human participation is necessary. Additionally, famous physicists occasionally speculated about the role of consciousness, sparking philosophical debate. While these ideas are intriguing, they are not required by the physics itself. Quantum mechanics works perfectly well without assuming that minds cause collapse. Observation in physics is simply a well-defined interaction that transfers information from the system to something else. To summarize, observation in physics is fundamentally different from everyday human observation. It does not involve attention, perception, or awareness. Instead, it involves a physical interaction that produces a measurable effect. Any measuring device, detector, sensor, or even environmental interaction can count as an observation in the technical sense. This understanding clarifies many mysteries of quantum mechanics and allows physicists to design experiments, develop technologies, and interpret results without invoking consciousness. This principle has profound implications for technology and philosophy alike. In quantum computing, for example, measurement is used to extract information from qubits. Engineers rely on detectors and readout mechanisms rather than human observers. Similarly, in quantum cryptography, information about particles can be transferred and recorded automatically, ensuring security based on the laws of physics. These applications depend entirely on the fact that devices, not minds, can perform measurement. Philosophically, it helps us separate the strange, counterintuitive predictions of quantum mechanics from unfounded claims about the human mind directly influencing reality. Quantum mechanics is one of the most successful theories in the history of science, yet it remains mysterious and counterintuitive. At its core lies the problem of measurement. How does a quantum system, which exists in a superposition of multiple possible states, collapse into a single definite outcome when observed? Most interpretations of quantum mechanics focus on physical interactions, detectors, sensors, or environmental interactions, as the cause of wave function collapse. However, a few interpretations have raised the provocative idea that consciousness might play an indirect, though not necessarily direct, role in the measurement process. This notion does not suggest that consciousness directly causes quantum events, but that awareness or information processing may influence how outcomes are recorded, perceived, or interpreted. Exploring this idea provides insights into the philosophical and conceptual depths of quantum theory. In classical physics, observation is straightforward. Measuring the position of a planet or the velocity of a car does not change the system in any significant way. Observation is passive, and reality is assumed to exist independently of who observes it. Quantum mechanics, however, challenges this assumption. Quantum particles, such as electrons or photons, exist in superpositions, states where multiple possibilities coexist simultaneously. When measured, the superposition appears to collapse, producing a single outcome. This collapse of the wave function is central to the quantum measurement problem. Most physicists agree that measurement involves a physical interaction with a system. For instance, a photon striking a detector or an electron interacting with a sensor transfers information from the system to the measurement apparatus, producing a definite result. Consciousness is not required for this process to occur. The results of countless automated experiments confirm that wave function collapse occurs even when no human observer is present. Yet, some interpretations probe deeper, asking whether consciousness might influence measurement indirectly, not by physically causing collapse, but by shaping the way information is realized, recorded, or utilized. One of the earliest proponents of this idea was the physicist John von Neumann, who formulated the mathematical framework of quantum measurement. Von Neumann demonstrated that, in principle, one could extend the chain of quantum interactions indefinitely. A particle interacts with a detector, the detector interacts with a recording device, and so on. Mathematically, the chain could continue to include everything in the universe, yet at some point, a measurement outcome appears definite. Von Neumann suggested that the final link in this chain might involve a conscious observer who becomes aware of the measurement result. While the physical interactions determine possible outcomes, consciousness could be the element that selects which possibility is realized from a subjective perspective. This approach does not claim that the mind forces reality to change, but that awareness plays a role in how a definite experience emerges from probabilistic possibilities. Another exploration along these lines is found in the ideas of Eugene Wigner. Wigner considered a thought experiment in which a quantum measurement occurs inside a closed laboratory, while the observer outside the lab does not yet know the outcome. According to standard quantum rules, the system, including the laboratory and the internal observer, is described as a superposition of multiple outcomes. Only when the external observer gains information does the system collapse into a definite state from their perspective. Wigner proposed that consciousness might act as the interface where probabilistic superpositions become definite experiences, even if the underlying physical processes proceed independently. This perspective emphasizes the relational aspect of measurement. Different observers may have different information, and consciousness plays a role in realizing the outcome in a subjective sense. It is important to stress that these interpretations are not mainstream physics. They are philosophical extensions designed to probe the boundaries of understanding. Modern quantum mechanics and quantum field theory operate entirely without reference to consciousness. Experiments such as quantum entanglement, teleportation, and automated double-slit setups demonstrate that measurement outcomes occur independently of human awareness. Nevertheless, the idea that consciousness could play an indirect role has persisted because it touches upon the deeper question: what is the nature of reality as experienced by a conscious observer? Some interpretations consider the link between consciousness and information. In these views, quantum measurement is fundamentally about the acquisition and recording of information. Consciousness is not necessary to produce a physical outcome, but it might play a role in interpreting that outcome within an experiential framework. For instance, a detector may record an electron's position, creating a permanent mark in the environment. The physical world behaves consistently, but the conscious observer interprets that record as a definite experience of reality. Consciousness, therefore, is indirectly involved in the sense that it forms the interface between recorded information and subjective experience. There are also theories in quantum cognition that speculate on the brain's sensitivity to quantum effects. Some researchers propose that quantum processes in neural microtubules or synapses could, in principle, maintain superpositions and influence information processing. While these ideas are controversial and remain largely theoretical, they exemplify how the concept of consciousness and quantum measurement can be explored scientifically. In this framework, consciousness does not directly collapse wave functions. Rather, it may exploit or interpret probabilistic information in ways that classical systems cannot. The emphasis is on the indirect role of awareness in shaping complex outcomes. Another reason consciousness is sometimes invoked is the philosophical question of subjectivity. Even if all physical measurements are deterministic or probabilistic, what we experience is always filtered through consciousness. In this sense, consciousness could be considered the final stage of realization of a quantum event. The event exists as a set of probabilities in the external world, but the conscious mind transforms these probabilities into definite experiences. This notion aligns with interpretations emphasizing the relational and informational aspects of quantum mechanics, rather than suggesting supernatural influence. Despite these explorations, it is critical to clarify that mainstream science does not require consciousness to explain any experimental observation. Automated detectors, computers, and sensors produce measurable outcomes that obey quantum rules perfectly. Consciousness is not necessary for quantum devices, quantum computers, or quantum communication systems to function. The indirect role of consciousness, if any, remains a conceptual question rather than a testable physical principle. Its study belongs to the intersection of physics, philosophy, and cognitive science. Quantum mechanics, developed during the early 20th century, radically transformed our understanding of the universe. Classical physics, which dominated science from the time of Newton through the 19th century, portrayed a universe that was predictable, objective, and independent of observation. According to classical laws, if one knew the positions, velocities, and forces acting on all particles in a system, one could predict its future with complete certainty. Reality was considered absolute. Objects existed with well-defined properties, and measurements merely revealed these pre-existing facts. However, quantum mechanics shattered these assumptions, introducing profound uncertainty, probabilistic outcomes, and observer-dependent phenomena that challenge the very foundations of how we understand reality. At the heart of quantum mechanics is the principle of superposition. Particles such as electrons, photons, and atoms do not exist in a single definite state prior to measurement. Instead, they occupy a range of possible states simultaneously. For example, an electron in an atom does not travel along a single, well-defined orbit as a planet moves around the sun. Instead, it exists as a cloud of probability, representing all the locations it could potentially occupy. Similarly, photons passing through a double-slit apparatus do not go through just one slit. They exist in a superposition of both paths until measured. Superposition challenges the classical notion of certainty because, in the quantum realm, properties such as position, momentum, and spin are not fixed until a measurement is made. Reality, at its core, is probabilistic rather than deterministic. The Heisenberg uncertainty principle further underscores the challenge to classical certainty. It states that certain pairs of properties, such as position and momentum, cannot both be precisely known at the same time. The more accurately one measures one property, the less precisely the other can be known. This is not a limitation of instruments or experimental skill. It is a fundamental property of nature. The universe does not allow both pieces of information to be determined simultaneously. Classical physics assumed that uncertainty arose only from measurement imperfections, but quantum mechanics reveals that uncertainty is intrinsic. This realization forces a reconsideration of what it means to know something about the physical world. Quantum mechanics also challenges classical ideas of reality itself. In the classical world, objects possess definite properties independent of observation. An apple is red whether or not anyone looks at it. A planet exists in a specific orbit even if unobserved. In contrast, quantum mechanics suggests that some properties of particles do not exist in a definite state until measured. The act of measurement does not merely reveal the property, it helps define it. The famous double-slit experiment illustrates this vividly. Electrons fired toward two slits produce an interference pattern when unobserved, behaving like waves. When measured to determine which slit they pass through, the interference disappears, and the electrons behave like particles. The experiment demonstrates that observation affects reality at a fundamental level. The line between what exists objectively and what exists only when measured becomes blurred. Entanglement further complicates our understanding of reality. When particles become entangled, their properties are linked such that measuring one instantly determines the state of the other, even if they are separated by vast distances. This phenomenon, described as spooky action at a distance by Einstein, appears to violate classical intuitions about locality and separability. In a classical universe, two distant objects cannot influence each other instantaneously. Yet quantum entanglement shows that particles are not independent entities, but parts of a connected system. Measurement on one particle collapses the joint wave function, defining correlated outcomes across space. This challenges classical notions that reality is composed of isolated, independent objects with predetermined properties. Quantum mechanics also redefines the role of perception. In the classical view, observation is passive. Scientists merely look at the universe and record what exists. Quantum theory, however, shows that measurement is an active process that interacts with the system. When we measure a particle's position, we inevitably disturb its momentum. When we detect a photon's path, we collapse its wave, like superposition. While this does not mean that consciousness directly affects reality, it emphasizes that observation cannot be completely separated from the phenomena being observed. Perception, in the form of measurement, plays a participatory role in the creation of outcomes, altering our classical understanding of the observer as a passive witness. The probabilistic nature of quantum mechanics also has profound philosophical implications. Classical science suggested that, in principle, all events were predictable. Quantum mechanics replaces this certainty with probability distributions. A particle's location, energy, or spin is described by a wave function, which encodes the likelihood of each possible outcome. This shift forces a conceptual change. Science is no longer about predicting exact outcomes with absolute certainty, but about calculating probabilities and understanding trends. It redefines the meaning of knowledge, precision, and causality. Furthermore, the very nature of time and sequence is questioned in the quantum framework. In classical mechanics, cause precedes effect in a clear and predictable order. Quantum systems, however, can exhibit correlations that seem non-classical, particularly in entangled systems. Events that are measured can influence the possible outcomes of distant systems in ways that are probabilistically connected, suggesting that our intuitive notions of linear cause and effect are incomplete when applied to the quantum world. These challenges have influenced not only physics, but also philosophy and cognitive science. Questions arise about whether reality exists independently of observation, whether probabilities are objective features of the world or merely expressions of knowledge, and how our perceptions shape what we understand as reality. While most physicists maintain that consciousness is not required for physical processes, the participatory nature of measurement highlights that knowledge and observation are inextricably linked. Reality at the quantum level cannot be fully separated from the acts of measurement and information acquisition. Finally, the shift from certainty to probability, from independent reality to observer, influenced outcomes, and from passive perception to interactive observation has profound technological consequences. Quantum mechanics underpins the design of semiconductors, lasers, quantum computers, and quantum communication systems. These technologies exploit the very phenomena that challenge classical intuition, superposition, entanglement, and wave-particle duality, to perform tasks that would be impossible in a purely classical world. The abstract conceptual challenges of quantum mechanics translate directly into practical innovations, showing that understanding and embracing these counterintuitive principles has tangible benefits. The observer effect encourages deeper reflection on the connection between knowledge and existence. The observer effect in quantum mechanics is one of the most intriguing and philosophically profound phenomena in modern science. At its core, the observer effect refers to the principle that the act of measuring or observing a quantum system can influence its behavior. Unlike in classical physics, where observation is largely passive and does not disturb the system, in quantum mechanics, the very act of acquiring information about a system alters its state. This subtle yet fundamental feature of reality has implications not only for physics, but also for philosophy, epistemology, and our understanding of existence itself. It encourages deeper reflection on the relationship between knowledge, the information we acquire about the world, and existence, the nature of reality independent of observation. To appreciate the significance of the observer effect, consider the behavior of quantum particles such as electrons or photons. In experiments like the double-slit experiment, particles can display both wave-like and particle-like characteristics. When unobserved, a particle behaves like a wave, passing through multiple paths simultaneously and creating an interference pattern. However, the moment a measurement is made to determine which path the particle takes, the wave-like behavior collapses and the particle behaves as a discrete object, producing a pattern consistent with classical expectations. The mere presence of a measurement device, regardless of human consciousness, changes the outcome. This shows that knowledge about the system, obtained through measurement, is inseparably linked to how the system manifests itself in reality. The observer effect encourages reflection because it challenges the classical assumption that reality exists entirely independently of our knowledge of it. In everyday life, we assume that objects have fixed properties whether or not we observe them. A tree, a mountain, or a planet exists with its characteristics intact, regardless of whether a human perceives them. Quantum mechanics, however, reveals that at fundamental scales, properties like position, momentum, and spin are not definite until measured. This does not mean the universe depends on human thought, but it does suggest that the existence of certain phenomena is revealed, defined, or realized only when information about them is obtained. Knowledge and existence are intertwined in ways that were unimaginable in classical physics. One key concept that illustrates this connection is the wave function. A wave function mathematically describes all possible states of a quantum system and assigns probabilities to each outcome. Before measurement, a particle exists in a superposition of states. It is in many possibilities simultaneously. Only when the wave function is observed or interacts with a measurement apparatus does it collapse into a single outcome. This collapse represents the transition from potentiality to actuality, from abstract probabilities to concrete facts. The act of gaining knowledge about the system, the measurement plays a defining role in determining the observed state. In this sense, knowledge is not merely passive. It is a mechanism through which possibilities are transformed into actualized realities. The philosophical implications of this are profound. If reality at the quantum level depends on interaction with a system capable of recording or transmitting information, then knowledge becomes a bridge between the abstract potential of existence and the concrete manifestation of phenomena. This challenges us to rethink the traditional distinction between observer and observed. While classical thought treats reality as independent and knowledge as a mirror reflecting it, the observer effect suggests a participatory universe where the act of inquiry itself is an integral component of existence. The universe is not a static backdrop, but an active, responsive system in which information plays a foundational role. Furthermore, the observer effect raises questions about the limits of certainty. Classical physics promised predictability. If all forces and initial conditions are known, the future can be determined with precision. Quantum mechanics, reinforced by the observer effect, replaces certainty with probability. The precise behavior of individual particles is not fixed until interaction occurs, and measurement outcomes are inherently probabilistic. Knowledge does not merely reveal a pre-existing reality. It participates in defining which potential reality becomes manifest. This suggests a subtle interplay between epistemology, the study of knowledge, and ontology, the study of existence, emphasizing that the two cannot be completely separated in the quantum realm. The observer effect also finds echoes in thought experiments that explore the conceptual limits of observation. Schrödinger's cat, for example, illustrates a system in superposition, a cat that is simultaneously alive and dead until the box is opened. Opening the box is a form of measurement, collapsing the superposition into a single reality. While this is an idealized scenario, it serves to highlight how gaining knowledge through observation or interaction determines the realized state of a system. In essence, the boundary between the observer and the observed is less rigid than classical intuition suggests. Existence is not fully independent. It is partially contextual, defined in relation to what can be known about it. This reflection extends beyond philosophy into practical applications. In quantum computing, for example, qubits rely on superposition and entanglement to perform multiple calculations simultaneously. Measurement is used strategically to extract information from the system. The very act of acquiring knowledge, reading the qubit's state, collapses its wave function, determining the output. Engineers must carefully design when and how measurement occurs, demonstrating that knowledge is not merely passive but a tool that shapes outcomes. This interplay of observation and effect underscores that in the quantum world, the acquisition of information is inseparable from the realization of physical states. Another dimension of reflection concerns the broader interpretation of reality. The observer effect encourages the perspective that reality is dynamic and participatory rather than fixed and detached. While everyday macroscopic objects appear definite and independent, quantum mechanics reveals that at the foundational level, the universe exhibits probabilistic behavior, interdependent states, and outcomes that crystallize only when observed or measured. This invites a philosophical shift. Rather than assuming that reality exists entirely independently of our knowledge, we recognize that the process of knowing is entwined with the very structure of existence. Importantly, the observer effect does not imply that human consciousness is required to create reality. Measurement can be accomplished by any physical interaction, including automated detectors, sensors, or environmental interactions. The effect is about information transfer, any process that converts a superposition of possibilities into a definite, recorded outcome counts as an observation. This distinction clarifies that the connection between knowledge and existence is structural rather than mystical. Reality manifests itself in response to the acquisition and recording of information, whether by human or machine. In conclusion, the observer effect encourages deeper reflection on the connection between knowledge and existence because it highlights the fundamental interdependence of measurement, information, and reality. Unlike classical physics, where observation simply reveals what already exists, quantum mechanics shows that gaining knowledge plays a role in defining what becomes real. Superposition, wave function collapse, and the probabilistic nature of quantum events illustrate that reality is not fully independent of interaction. Observation, broadly defined as any information, acquiring process, mediates the transition from potentiality to actuality. Philosophically and scientifically, this insight challenges classical notions of a detached, objective universe, encouraging us to appreciate the participatory, interconnected, and probabilistic nature of existence at the deepest levels. Knowledge is not merely a reflection of reality. In the quantum realm, it is an essential factor in shaping the very fabric of what exists.